this side Mayank Jain, and today I'm here to explain my core ledger engine project, which is a financial ledger system which is built using exact same accounting and engineering principles that power real world banking applications. So let's deep dive into that. First, we have our Docker image file. Our Docker image contains exactly six containers that those are of main database, and the second one is of the in-memory database, the Redis. Then we have pgadmin Postgres web client to see our database records in real time for production purposes only. And then we have two application instances which can be horizontally scaled and can be increased further as per our traffic requirements. And then we have our Nginx reverse proxy, whose main job is here is to do load balancing and prevent our application from various attacks like clickjacking, DDoS attack, and X header forwarding, and much more attacks like that. Let's talk about our system architecture. So first, the request which is coming from the browser postman goes to Nginx reverse proxy. Note, it never goes to the main application. First, it will meet the Nginx reverse proxy, who will do load balancing using the round robin algorithm, and the traffic will be shared across these two application instances, which will proceed further with our business logic. So now let's talk about our main five features of this project. First one is the double entry bookkeeping. So let me sign in first. So I am currently signed in with this username. So every request after this needs a valid JWT token. I will come back to the auth flow in a second. Now we'll make a transfer. So I will be making the transfer from the account that I am currently logged in to some other account, and we can say the transfer is successful. So initially we have some ledger entries. As we can see, we have five ledger entries for this account specifically. But if I just run this again, now we have six entries, and this current entry shows that 100 rupees was deducted from this account. But the main feature here is that we have exactly two entries. So if I just see all the ledger entries, uh, we will be having two entries exactly. One is for the account from which the money is deducted, and one is of the account in which money is transferred. So the net balance here is minus 100 plus 100. The net balance comes out to be zero, which represents the money is never created nor destroyed. It just moved from one account to other. That's how basically bank works. And next, if you see, every row has two columns. One is of the hash and one is of the previous hash. So what are those exactly? That is our second feature, the blockchain style audit trail. So each ledger entry contains a SHA-256 hash of its own data. These hashes are created using the balance of the account. Sorry, not the balance of the account, the amount of this ledger, the amount transferred, the mentioned in this ledger entry, the transaction ID or the reference ID of the transaction, and the timestamp at which this ledger entry is being created. So these hashes are generated using those three attributes, and it's the same principle as blockchain, built from scratch without any blockchain library. If you see the previous hash here, let me just so these are the ledger entries for this account specifically. So here, if you see the previous hash of this row, it is exactly same as the previous hash of the last ledger entry. So you see what happened here. That's a chain. If anyone goes into the database and manually changes the amount, let's say here he set 1500 to 1.5 million, what will happen? The entry hash breaks, and every entry after this becomes invalid. So an database manager or a system admin can verify where this ledger entry is broken. So we will see that as well. We have some thing called a audit API, audit endpoint, for it's specifically for the system admin. Let me sign in as the system admin as of now. I will just get the JWT, and then I will run the audit trial for this account specifically, and the account ID is this. I will just copy it from here, paste it over here. I will just run it, and it says valid and broken at null. That means the current ledger chain or ledger entries are valid. But what if some rogue database admin or a hacker get the access of this database and he sets this 1500 to 1.5 million or something? Then what will happen? Let me show you that as well. As you can see, I made a change and I updated the amount for this ledger entry. So now what will happen if a system admin runs an audit trial for this account? The Our algorithm says the corrupted data modified and broken at this ledger entry specifically. So admin will be able to get the knowledge where this chain is actually broken, and he can just verify it with some other record and fix this chain. So the next feature is of optimistic locking. So I want you to imagine a scenario in which a single account is logged in into two devices, two mobile devices, and the amount in that account is, let's say, 1,000 rupees. And these two mobile devices are operated by different person, but the account logged in is same. So what if two transfer requests are made from both these accounts at the same time? One request says, let's say, let's transfer 700, and another one say, let's transfer 500 rupees. And both these requests are valid because 700 is less than 1000 and 500 is also less than 1000. Both these requests are valid and will be processed. So but they are happening at the same time. So the net amount deducted will be 1200, 700 plus 500. But wait, this is wrong. The total balance was only 1,000 rupees only. So where this money is created? So we can see the money is created out of nowhere. So to protect this, we use concurrency and optimistic locking. So what is optimistic locking? Basically, every account is have a column called version. This is a version counter which is handled by Hibernate, and it increments every time when this row is basically updated. So let's say initial both requests come at the same time. Database will log the request in the nanoseconds or whatever in the deepest level. One thread will be processed at a time in the database. So initially what will happen, the first request will say, hey, I want to update the balance of this account where the version is 8. Initially the version is 8, and this will update the account and the version will be set to 9 now. So the next request that is coming at the exactly same time knows the version of this account is 8, and it will say, hey, now let's update the account whose version is 8 now. But it will not be able to find the account because the account is updated to 9. So as we can see, the transfer will not be valid for the second thread that is coming. So only one request was validated, and the request that failed will fall back into the retry logic that is handled by the Spring Boot retry logic. We will discuss about that later on. So to demonstrate this process, I have created a something called hacker attack. So this scripts basically fire multiple threads at a time for the same account. It send multiple transfer requests at the same time. And every request say wants to transfer 1500 rupees. Sorry, here it is the attack, and every thread says let's transfer 1500. So if I just fire this let's see what happens. So basically 9 requests were made at the same time. So 15 into 9, that is 135. So the net money deducted should be 13,500. But if I just go to my account section, and here initially the balance 8700, if I just hit it again, only 1500 rupees should be deducted, not 13,500. And we can see the only 1500 was deducted. So our optimistic locking is working perfectly fine, and the version is updated to 9 only. So this is this optimistic locking feature. Next comes the idempotency feature. I want you to imagine a scenario in which you were making a transfer request and you were about to click on pay button. You clicked on pay and suddenly your internet gets stuck or the server crashes. And out of rage, you just spammed that pay button multiple times. So what will happen in that scenario? Multiple transaction requests can be generated, but it should not be happening. You only want to generate one transaction request. So to tackle that, we have something called reference ID tied to every transaction is generated, and this reference ID is basically assigned from the front end to each and every transaction. So if you spam that if you spam that pay account multiple times, the reference ID for all the transaction will be same, and we will get to know that, hey, this reference ID already exists and this is a duplicate transaction. Do not process it. I will show that to you as well. If I just make a transaction of the transaction ID 3, which is already existing, so here have a look what it says. 409 conflict, transaction 3 already exists. So it says it's a duplicate transaction and cannot be processed further. Next feature is of the Redis part. Redis is basically performing two main things here. One is of the caching and another one is of the distributed rate limiting. First, let's talk about the caching part. So this get balance API, whenever I fire this API, what will happen that it will fetch the balance from the database and store that balance for a particular amount of time, currently 10 minutes in in this scenario, in the in-memory database called Redis. So if I just fire the request, this 7200 money was fetched from the database and will be saved to Redis for the next 10 minutes. So if I just fire this request again, now we won't be making a, direct database call. Instead, we will be fetching this balance from our cache memory, that is from the Redis. If I will just show you that, uh, these are all the logs of our application that is running. Cache it, we can see the returning balance from the account ID this. So cache hit, Redis was acted in this scenario. So Redis is playing as a in-memory database for this. And the second feature that Redis is implementing is of the distributed rate limiter. So basically, what is a rate limiter? It prevents our application from DDoS attacks like spamming and going bot spamming all the requests from the multiple APIs. So it protects our application from that and our application from crashing. So for this, our Redis rate limiting service have exactly two buckets. One is of the transaction type and another one is of the general type. So all the APIs like this transaction API, deposit, withdraw is protected by this transaction bucket. This transaction bucket follows the classic bucket type, classic refill strategy. It says one token is allowed per minute. That means one user can just do one transaction per minute, and the REST APIs like get balance and get statement and all the other APIs are protected by this uh, second bucket, which is the lazy bucket or the general bucket, and it follows the greedy pattern. It says 10 requests per minute, and it follows greedy approach, which is a burst approach. Like all the tokens will be given instantly in that bucket. Right, so I will just show you that as well. I will just do a cheap DDoS attack, a manual DDoS attack on this get balance API. It is implementing the general bucket like 10 tokens per minute, and if I just spam over and over, ultimately it will just throw us this error, too many requests, please wait a minute. So our Redis rate limiting is working absolutely fine. The main feature of this rate limiting is it follows a distributive pattern. So we currently have two app instances, and if it doesn't matter from which app instance the user is making the request, the bucket is common for both these instances. It has one common Redis bucket, and the tokens will always be fetched from that bucket only. And if you will say, let's say both the instances make request at the same time, what will happen then? In that scenario, our Redis will always also follow something called scarce, compare and set based strategy. It is also kind of optimistic locking. I will show that to you as well in the Redis configuration. It follows bucket forge lettuce.cast based builder. So it also follows a optimistic locking kind of pattern to completely implement the distributed rate limiting service. So these are the main features of my application. Well, it contains much more part like logging. It contains debug level logs. You can see right here the debug level logs at each and every API. And then we have GitHub Actions, GitHub CI/CD for the commits and changes made into our repository. And then we have Nginx reverse proxy, which is handling many different tasks from headers to everything, CORS protection, and much more protection like that. So this was my whole project. Thank you guys for listening to me. If you like this project, like my hard work, so please drop a like. It will I will much appreciate that. And thank you for listening.